Adimurthy. So it's my pleasure to be here talking to you, and I owe this pleasure to the hosts, Rukmini Loganayagam and Professor Adimurthy, for organizing this wonderful conference. It's more a discussion meeting, and I've learned quite a lot about the mathematical side of Noether's work in the last few days, and also something about her personality. Now, what I want to do is to follow up on yesterday's talk by Professor Mukunda and say the same thing in a slightly different language with a slightly different perspective. And you'll find some repetition in some ways it's a repetition and in some ways it's not. So from that point of view, it'll be easier for the mathematicians to follow my way of explaining the same thing. But I'll also talk about a few other things, like some of the sociology involved and some of the personal aspects to this story. So the first thing you'll notice, before I start, I'll just make a quick summary of the talk, the different topics I'm going to cover. So this is written on the other side, and you will not need it. So let me start with the introduction. You might have noticed that I put the S in red here, theorems. And Noether's paper actually contained two theorems. And that's an important part of the story because in physics, we always learn about Noether's theorem. And the S was lost in a translation. There was an edition of Courant and Hilbert in German, which used the plural. And the English translation does not have the plural. And this has caused us to think of Noether's theorem as essentially the first theorem and giving less importance to the second theorem. And that's a pity, as that's one of the themes I follow. So Noether's work on symmetries and conservation laws for variational problems was a paper published in 1918, although as we have seen, the work was actually done 3 years earlier in 1915. Now, this is a work that was motivated by a question raised by Hilbert. And it was a very general piece of work, and it was forgotten within a few years. For a few years, there were references to it, and then after that, it kind of disappeared from the consciousness. It reappeared in truncated form in the 50s, and only in the 1960s, 70s, and 80s did physicists appreciate the full power and generality of her work. And the influence in physics is still continuing today, and that's basically the reason for my title. So one of the questions I'd like to address is, why did it take so long for all these ideas to permeate into physics? And I've already put the summary of the talk over there. The question is, why so little impact in physics? It could have been absorbed into the physics consciousness much earlier than it was. The brief answer is that at that time, in the 1910s, the power of variational principles were not fully appreciated by physicists at that time. So there were two theorems. The first theorem deals with what I will call symmetries of the first kind. This is more in accord with modern physics notation than Noether's own classification. This consists of transformations which depend on parameters. There was also symmetries of the second kind, transformations depending on arbitrary functions. I'll give an example of each of these. Suppose you have a function phi, which is defined on space-time. This is a coordinate in space-time. And you make a variation, delta phi is equal to I epsilon times phi of x with parameter. This is an example of a symmetry of the first kind, which depends on a parameter. And if you write down the following action, which is called the Klein-Gordon action, I'll explain these terms in a few minutes. This is a complex scalar field. You find that this function is invariant under transformations of this kind. However, you can make more general transformations. You can make a transformation where phi of x goes to I epsilon of x, where this is an arbitrary function of space-time, times phi of x. And under this transformation, this function is not invariant. It doesn't stay the same. So these are symmetries of the second kind, which depends on an arbitrary function, in this case, epsilon of x. Yes, it is. In fact, yeah. So if this is a constant, it's a transformation of the first kind. It's true. What you're saying is true. And that will also be part of the story towards the end when we get to gravitational energy. Yeah? So the difference between these two is that here you have an arbitrary function. It should be true under not just a fixed epsilon, but an arbitrary function. And here it's only, the variation demands that epsilon is a constant over space. Yes?
Usually the epsilon of x.
Yes. Yeah. Yeah. Yeah, we'll come to that also. Yes, yes, yeah. That's also a relevant remark. Yeah. All these things will come up again in the sixth part when we talk about gravitational energy. Now, in the 50s, Edward Hill, who was a physicist in America, in Minnesota, he presented a simplified version of Noether's work for mathematical physicists, in which he talked only about theorem 1 and not about theorem 2. And this led many physicists to believe that Noether's theorem consisted entirely of theorem 1. And it's not fair to blame Edward Hill for this. At least he did the job of putting across theorem 1. But if he had put across both the theorems, we would have been better off today. Physicists of the time latched on to theorem 1 and quoted it as the Noether theorem. And that's why we lost the second part, which is extremely relevant, as you will see. Now, there's a quotation attributed either to George Bernard Shaw or Oscar Wilde that the US and England are two peoples divided by a common language. The same can be said of mathematicians and physicists. There's a lot in common between mathematicians and physicists. They sort of use the same language, but there's definitely a communication gap between these two communities. And this is also responsible for a lot of the slippage between Noether and physics. Michael Atiyah urges mathematicians to study physics, but also presents them with the harder task of understanding physicists. It turns out that physicists use a language which is slightly different from what mathematicians use, although they're sometimes dealing with the same concepts. And conversely, the rigor and generality of mathematical treatments is often a barrier to physicists absorbing them. So these are bridges that we have to make between the two communities, and I think this conference goes some ways towards making those bridges. Now, mathematicians are often mystified by the language used by physicists, and I will give two examples of this and use these to explain those words. For example, the words action and field theory mean something else to physicists, to mathematicians, than they mean to physicists. The word field theory, for example, we heard a lecture about it yesterday from Professor Kanduja, and that had to do with a mathematical structure which is known as a field. What we call a field is slightly different. I'll explain that, and I already used the notion here. The word action in mathematics talks about group action on a manifold. But for some reason, historical perhaps, physicists use the word action in a different way. So fields are usually functions on space-time. The space-time variables are the independent variables, and the functions are dependent variables, like this phi here. If you want to be slightly more fancy, fields are sections of vector bundles over space-time. There are also other more general fields which are not vector bundles. For example, connections are also treated as fields, and also maps between manifolds. That happens in a class of theories called sigma models, which are interesting in physics. And also in string theory, it's a map between a world sheet and space-time. A physicist's theory is determined by a set of fields and an action principle. An action principle is what we use for the variational principle, which gives rise to the equations of motion. Once we write down a set of fields and an action principle, we have a theory. The challenge then is to work out its predictions. And the final objective is not to just have a theory, but to test these predictions by whether they give a good description of nature, in the sense that they should agree with experiments. There are experiments done in colliders, spectroscopic experiments, many different classes of experiments can be explained by a small set of theoretical ideas. So the tendency in physics is to have a large set of predictions, if possible, from a small set of fundamental principles. Now, I get to the second part, variational principles in physics. You can express mechanical laws in terms of forces, which was done by Newton, or you can use a variational principle, and such a variational principle was given by Lagrange. And actually, this has a long history. It goes back to Hero of Alexandria, who noticed that if you have a mirror, the law of reflection, which tells you that the incident angle is equal to the reflected angle, this law can be derived from a variational principle. What you can do is to basically, in a formal sense today, reflect this about that, and notice that the shortest path between this and that is actually a straight line, and reflecting that back gives you the law of reflection from mirrors. So Hero of Alexandria knew that physics can be described by variational principles. Now, the same idea was used by Fermat to explain refraction. Refraction has got a completely different law of the incidence angle and the refracted angle are related by the sign of the refractive indices. Nevertheless, you can unify all these different laws under one formulation that was given by Fermat, that light travels from A to B in order to reach in the least time. Fermat's least time principle is a variational principle. This was about in the first century.
At that time, they even know that light travels. They know that light has a finite speed.
No, they didn't need to know that light has a finite speed. They were, so Hero was talking in terms of distances. So at that time, distances translated into, he gave the principle in terms of least distance. Fermat translated into least time. The shortest path.
I'm asking if they got of it as a path that happens over time, or as just something that already, like it's not on the light, but
yeah.
the idea that the light travels and it always stops.
No, time was absent in this description. It was purely space, but it was still a variational principle. But when it came to Fermat understood time as well as space. Yeah. Of the first century, like about 70. He died in AD 70, so somewhere around. AD, Anno Domini. So soap films, for example, you can either talk about the configuration of soap films by using force balance or by minimizing energy. Now, you will agree that the minimization of energy is a much more compact and simple way of describing the forces that keep a soap film in place. In the 1910s, it was not at all obvious that physical laws could or should be expressed as variational principles. So that was the psychology at that time, that they wanted to write down physical laws, but they didn't necessarily believe that it came from a variational principle. So Einstein, for example, was not convinced of the need for a variational formulation. He was looking for equations of motion in tensorial form. And in this quest, he was governed by the fact that he had some physical ideas, the principle of equivalence. He also had some philosophical ideas that came from Ernst Mach. And he wrote his equations. First, he arrived at the form Ricci tensor equals matter tensor. So that can be written as in Riemannian geometry with a constant here. So this constant is about Newton's laws. I mean, it occurs in Newton's laws, the gravitational constant. This is the stress energy of matter, which is the source of gravitation. And the Ricci tensor is a purely geometric object constructed from the Riemannian metric. So this form is actually incorrect, and it satisfies the idea that the equations of motion are in tensorial form, but it cannot be derived from a variational principle. Had he restricted himself to variational principles, he would have not made the mistake of writing down this form of Einstein's equations. And neither was Pauli a believer in variational principles. So the resistance to this idea of a variational principle could have been due to dissipative systems. For example, there are some which generate entropy. If I rub the chalk on the board, for example, heat is produced, and such processes generate entropy. And the use of variational principles is actually restricted to those situations where you don't have dissipation. And in fact, thermodynamics and non-equilibrium thermodynamics was an important part of their thinking in those days, because thermodynamics is what threw up quantum mechanics in the early 1900s. So the resistance must have been due, I'm guessing, due to the fact that not everything can be described by a variational principle. However, there are many good examples. Newton's planetary system has negligible dissipation, and also atomic physics, which was being developed around the same time, also has no dissipation. Now, Hilbert was a mathematician, and he did not have this particular hang-up. He wanted to use a variational principle to derive Einstein's equations, and he wrote down the simplest possible action, which is now called the Einstein-Hilbert action. Where this is the Ricci scalar, and when you require that the Einstein-Hilbert action is stationary with respect to variations, you find that you get the right equations of motion. Which differs from the incorrect one by just this extra factor, which will turn out to be important later. Klein, who is another mathematician, he dismissed Hilbert's fanatical belief in the variational principles, the view that one can describe the reality of nature by purely mathematical considerations. He was not convinced, although he was a mathematician, that mathematics was going to be a guiding principle in physics. And this connects to another statement by another great physicist, Eugene Wigner, who has always talked about the unreasonable effectiveness of mathematics in physics. You think it does not work or it should not work, but in fact it does work. So variational principles provide an elegant restatement of the laws of physics. In statics, the minimization of energy tells you the configuration of bodies. For example, the pendulum hangs at its lowest point. In mechanics, we have the Lagrangian formulation. In optics, Fermat's principle of least time. In field theory, we have the action principle, which I gave an example earlier. Now, in equilibrium statistical mechanics, we minimize the free energy, and it still works. But variational principles don't really seem to work in non-equilibrium statistical physics, and that is still an open problem. People are working on trying to find variational formulations for non-equilibrium situations. Now I come to the third topic, which is symmetries. I've just done with these two. Now Hermann Weyl gave a beautiful definition of symmetry. Well, not a definition, but is an idea by which man through the ages has tried to comprehend and create order, beauty, and perfection. I think man should include woman as well, since we're at Noethers. Now, it entered mathematics through the study of symmetries of differential equations, and this was talked about yesterday by Professor Lakshmanan, but it has always been there. In architecture or in design of gardens, one always likes to have symmetry. In the quantum theory, Eugene Wigner was one of the people who was very influential here. The mathematical machinery of group theory entered physics in a big way. In fact, in such a big way that many physicists complained about what they call the group and pest. Every discussion in physics ended up as a conversation about groups and their representations, and many people would get irritated with this and leave the room whenever the discussion started on groups. In fact, Landau, who's a tremendously mathematically able physicist, had initially, when I say Landau, I mean the physicist Landau, not the mathematician Landau. He had absolutely no idea about group theory until he realized it was useful. And then he went out and basically rediscovered everything by himself. I mean, worked it out for himself rather than look at the mathematics books. That was his normal tendency. Now, Noether's work deals with the intersection between variational principles and the theory of Lie groups. Neither of these paradigms had been assimilated into the physicist's thinking. And this might explain why physicists were not ready for this idea. So it makes the basic point that Noether was far ahead of her time in physics. Now, the attitude towards symmetries can be capsulated in Felix Klein's Erlangen program. This is a program which classifies geometries according to the symmetry group. And I'll only talk about the connected component of the symmetry group because that's all that's relevant to Noether. For example, in plane geometry, which has been there since Euclid, the symmetry group is ISO2, which means rotations and translations in the plane. And that is also called the Euclidean group. In spherical geometry, the geometry of the sphere, we talk about the rotation group because that is the relevant symmetry group for the sphere. And in hyperbolic geometry, it is variously described as either PSL2R or SO21, the orthogonal group which preserves an indefinite kind of metric. And it's interesting that a similar attitude in physics has emerged about the symmetries of space-time. For example, in Aristotle's time, it was thought of as space is a Euclidean space, E3, and there's a time which is an E1. Now, the set of transformations that preserves this structure is called the Aristotelian group, and it's got dimension 7. There are 3 rotations and three translations in space, and 1 time translation, the total dimension being 7. It's an affine space in the sense that the tangent space at any point is isomorphic to the whole space. Well, it's called Aristotelian not because Aristotle knew anything about affine structures. We're just putting his ideas about space and time in a present mathematical footing. Okay, so it has 2 important notions. One is a notion of time. We can talk about now all over space. I can talk about time as being a certain notion of simultaneity all over space. I also have a certain notion of here. This point of space for all time makes sense in Aristotelian space-time. And this point of, I mean, one second, can I explain this point, please? So this is space and this is time. So this is a notion of now, all points which are simultaneous with that. And this is a notion of here. Both here and now separately make sense in Aristotelian space. Yeah.
So the dimension of the space-time is 4, the symmetry group.
Yes, right. Now, in Galilean space-time, it is still an affine space, but instead of having a cross product between space and time, what we have is an E3 bundle over E1 that's slightly less structure. When you have less structure, the dimension of the symmetry group increases from 7 to 10. You get some extra transformations which correspond to, okay, the difference between Aristotelian and Galilean space-time is that here there's a standard way to identify points at different fibers. But there is no canonical identification between different fibers. There's no fixed notion of here. For example, if I'm sitting in a railway compartment, my whirl line will be like this. So here now will mean these 2 points are at the same location in space. So we have given up some structure and we have gained its symmetry, and that's the idea here. And the difference between theorem 1 and theorem 2 is an enormous gain in symmetry. We'll come to that later. So, sorry. The Galilei group now has got dimension 10 because there are 3 velocities which you can use as extra parameters in the symmetry of this structure. And Minkowski space-time is basically the symmetry group of space-time with an indefinite metric, a metric of signature minus plus plus plus. That's called the Poincaré group. It consists of Lorentz transformations, which are 6-dimensional, plus 4 translations. That has got the same dimension as the Galilei group, but the group structure is different.
Galilei
Yeah, Galilean is the same as Newtonian. But yeah, right. Newtonian space-time, you could call it that also. All these names are just invented a posteriori to distinguish them from each other. I'm sorry? Well, very recently, after relativity, they went back and tried to look at the evolution of structure of space-time over the centuries. Yeah. So these days, we characterize the physical theory by its symmetries. And in fact, when we're writing down, when we're looking for theories, it's often symmetry that's the guiding principle. So use symmetries to write down a variational formulation, that is an action. We have now agreed that we must use a variational formulation. Symmetries plus Noether's theorems give us conservation laws, which can be used to simplify the analysis of the equations of motion. Special instances of conservation laws were known earlier. For example, Newton's second law, I don't remember which law, but it might have been the second law, states that every action has an equal and opposite reaction. And that's basically an expression of the conservation of momentum. He also took, I'm sorry, it's the third law, is it? Okay. He also took Kepler's law of areas, and that's the conservation of angular momentum. So these two conservation laws were known earlier. And Lagrange knew about the conservation of energy. Okay? So these are special cases. But Noether's theorems formalize the connection between symmetries and conservation laws, and we get one for every conserved quantity, for every dimension of the symmetric group. So we actually get 10 of them, and not just 7 as we're getting here. Translation. Yes.
Two bodies collide.
Yeah.
Momentum is constant.
Right.
I'm wondering what the symmetry is.
Yeah, the symmetry is translation space. The homogeneity of space gives rise to momentum conservation from Noether's theorem.
What does it mean?
Well, if I have, suppose I have a Lagrangian, which depends on x. Let's say x, it's like this. Then the corresponding conserved quantity, according to Noether's theorem, is dl over dx dot, which is equal to mx dot. So it tells you that this quantity is conserved. And even if you have a system of particles interacting with arbitrary forces, provided the whole thing is invariant under translations, you find that the sum of the momenta is conserved. So the symmetries of space-time are those transformations that preserve the background structure. For a variation problem with symmetries of the first kind, one associates to every continuous symmetry of the space-time a conservation law. The Lagrangian formulation naturally induces a symplectic formulation of the cotangent bundle. And here, in fact, there's a connection with Hamiltonian physics, Hamiltonian mechanics, which Professor Mukunda talked about yesterday in great depth and length. And he was my advisor on my thesis, and if there are any questions on this topic, I'll reflect them to him. The conserved quantity is a function on the cotangent bundle, which is a fancy way of saying the phase space, which is the space of coordinates and momenta. And I should probably just give a slightly geometric version of the same idea before going on. So in classical mechanics, if you have a configuration space Q, the cotangent bundle consists of pairs which are points and cotangent vectors at that point. And this comes with a natural symplectic form defined in the following way. I define theta to be sum over I, pi dqi, where these are one forms and those are the corresponding momenta. This is the one form. I'll call this theta naught. And omega naught is defined as d theta. And omega is non-degenerate, and it's closed because of Poincaré's lemma. D of d is 0. We saw that yesterday in a different context. So omega, which is non-degenerate, means that Ix of omega naught equal to 0 implies that x is 0. All vector fields which annihilate this form vanish. and then d omega is equal to 0, means that the form is closed. So a closed non-degenerate form defines what we call a symplectic structure. And it comes naturally in the cotangent space without any Lagrangian at all. It's right there from the beginning. What the Lagrangian does is give us a map between the tangent bundle and, I should call it by some different name, between the tangent bundle and the cotangent bundle. And this gives us a symplectic formulation of classical mechanics that was not present without a variational principle, but in the Lagrangian formulation, all this comes for free. The conserved quantity is a function of the cotangent bundle. So given any function here, let's take a function h, for example. This formula, ixh of omega naught equal to dh. This is a well-defined equation. It's an algebraic equation that gives us a vector field on phase space, and that is called the Hamiltonian vector field corresponding to h. So what Noether's theorem tells us is that this h is conserved, and the same conserved quantity h generates a vector field which is the infinitesimal generator of the symmetry transformation. Now, all space-time symmetries are generated by such conserved quantities: energy from time translation, momentum from space translation, angular momentum from rotations or the isotropy of space, the boost generators from those extra symmetries that we learned of when going from Aristotelian physics to Galilean physics, because you can go to a uniformly moving frame and the laws of physics should stay the same. For electrodynamics, the action of electrodynamics is actually invariant under a larger group, not just the 10 spacetime symmetries, but there's a 15-parameter conformal group. These are conformal killing vectors, vectors that take the metric to a multiple of itself. And it turns out that Maxwell's equations actually have a larger symmetry than just the spacetime symmetries that we know from the groups that we talked about earlier. Now, these led to new conservation laws from Noether's theorem. They were not known before. And this was published by a student of Emmy Noether's whose name was Bessel Hagen. Now, for a variational problem of symmetries of the second kind, the corresponding conserved quantity vanishes identically. What happens is that this map, rather than being an onto map, which is usually the case for most Lagrangians, turns out to be an into map. So when you have a map that takes the tangent bundle into the cotangent bundle, should have been up there, then you have actually sigma, which is sitting inside T star of Q, as a submanifold in there. Then the pullback of this symplectic form to sigma, I'll call it like this, I sigma of omega naught. This is closed, but it need not be non-degenerate. It will have a kernel. Yeah. Yeah, yeah. Yeah, it's a function. It's a function on phase space, right? Yes, identically, exactly. So if you take this equation, you find that if you take a symmetry of the second kind, you'll find that this vanishes. So you have something which is in the kernel of omega. That's right. If you call it a charge, the charge is zero. The charge is a general term used for energy or angular momentum or anything like that. Yeah. I'm sorry? No, the charge vanishes identically according to Noether's theorem, symmetries of the second kind. So she has shown mathematically that the conserved quantity that you get from her theorem in the first part, that becomes zero. And that's an important idea which we are trying to explore further. So in fact, what you have is a kernel for omega, and you can show very simply that the kernel of omega is involutive. That is, if there are two vector fields, both belonging to the kernel of omega, then their Poisson bracket, their commutator, the Lie bracket between them, also belongs to the same space. So you find that the phase space splits up into leaves of a foliation, and it's the quotient space which is the physical phase space. So there are some arbitrary directions in evolution.
Integral also includes zeros.
Yes.
It's not necessarily a constant. Non-zero constant.
Yeah, it's
Also includes zero.
yeah. This is a function that vanishes identically. So it's not that, for example, if I take energy as a conserved quantity for the Kepler's law, the energy being zero is a special case, but there are all possible values allowed for the energy. Here it says that the function itself vanishes on phase space. Yeah. Now the theory of such Hamiltonian systems was worked out by Dirac. It was published mainly in the 50s, but he started thinking about it in the 30s. And he was one physicist who was quite happy to accept variational principles very early, because he was a more formal physicist, not quite a mathematician, but thinking like a mathematician in some ways. So this kind of symmetries happen in theories which gauge invariance or diffuse invariance. And diffuse invariance is the theory that originally brought out this problem through the work of Hilbert and Noether. But it also applies to a large class of other physical theories. In fact, between these two invariances, we cover all of modern physics. So consider the following simple model, which is a toy model for general relativity. If I take a point in R3, this is a particle whose position is defined by R3, and instead of using the usual Lagrangian, which I just erased, I will use the Lagrangian to be the speed of the particle. That is to say, the velocity squared to the half power. It's a legitimate Lagrangian one can use. Now this model has got a symmetry of the second kind. For example, it's homogeneous of degree 1 in the velocities, which means that if I take t and replace it by an arbitrary function of t, the action is invariant. And you find that in this case, the Hamiltonian vanishes, and it's a very simple calculation. This is what I was talking about. So time translation does not buy you anything more. So L is equal to half, not half, let's say V dot V to the half, dl over dv dot dv. This is the corresponding momentum. This is given by 2v dot v to the half. I would often put the vector signs, times twice v. And h is given by pv minus l. And if you work out pv, it turns out to be v dot v upon v dot v to the half. Minus L is just v dot v to the half. So that is 0. So this is an example of Noether's theorem 2, in which the corresponding conserved quantity for time translations vanishes identically. What is happening is very clear. The symmetry of this Lagrangian is so large that it includes time translations. And because the symmetry is so large, the corresponding conserved quantities all have to vanish, and that includes the symmetry of translations also. It's a subgroup. We find that the Hamiltonian vanishes, and this is an example of diffuse invariance on the world line. Now, there are similar ideas of diffuse invariance on the world sheet in string theory, and if you go to 4 dimensions, diffuse invariance of space-time is the symmetry of general relativity. Now, there was a time when Hermann Weyl was trying to unify general relativity with electromagnetism, and he put forward a theory in which you take a vector around a closed loop and you come back. Within Riemannian geometry, you require that the length of the vector is the same. Weyl's idea was that the length of the vector could change, and this change in the length of the vector could be used to code the information about the electromagnetic field. That is a brilliant idea, and it had geometrically and mathematically the very deep insights. Unfortunately, he did not agree with the experiment. And this was pointed out by Einstein, who turned around. Initially, he was very happy with this theory because it seemed to just take his own program further. But then when he realized he didn't agree with experiments, he was very much against it. But it had a mathematical structure that has remained in physics, the idea of gauge invariance. The word gauge actually comes from Eich in German, E-I-C-H in German. I'm not sure how it's pronounced, but that means the scales. So the scales are actually non-integrable. You can take a ruler, take it round in a loop and bring it back. And if you leave one ruler at home, you will find that the two rulers don't agree in size. Okay? So the path dependence of lengths was an idea due to Hermann Weyl. Weyl's idea that lengths could only be compared to the same location in space-time. Now this idea survives today in electrodynamics. Rather than the length, it's the phase of the wave function which is non-integrable. A slight change of physical emphasis, but the same mathematical ideas work. Now, symmetries of the second kind have come to dominate physics. Einstein's GTR threw up diffeo invariance, and in the 70s we had non-abelian gauge theories. In the 80s we had string theories, which also have a large amount of diffeo invariance, gauge symmetries in this form. These are described by a map from a two-dimensional world sheet to space-time. Diffeos internal to the world sheet are symmetries of the second kind. So the general idea is when we're looking for physical theories, we try to impose many more symmetries than we used to. As physics progresses, we go in for more and more symmetries. The idea of imposing more and more symmetries is that it cuts down the arbitrariness in our physical theories. Large symmetries means that we have much more tightly constrained theories. So that's the general trend in modern physics. And this trend was actually opened up by Noether's second theorem. So I think I'll just come to, I've got some time then. Maybe I'll pause here for questions on what I've said. I'm not very sure if I've got through in all the main points. Okay. So the genesis of Noether's paper was Hilbert's attempts to understand general relativity. When Noether was in Göttingen, Hilbert had this desire to understand Einstein's general theory of relativity. In fact, Einstein visited him at Göttingen, and the two hit it off famously, although they were from different persuasions, so to speak. Einstein was not so interested in the variational approach. Hilbert wanted to develop the variational approach. And the problem that turned out is that Hilbert was finding that the law of energy, which in German they call it, well, what they call the law of energy is the law of energy conservation in India, in English, didn't seem to make much sense to Hilbert. Anyway, he wrote up his paper and he asked Noether for help in understanding this problem, and that was the genesis of Noether's theorem. Now it turns out that we already talked about the diffeo group being the symmetry group of general relativity, and Einstein was actually struggling with this for quite a long time. So in fact, he tried other invariance groups. Rather than come up with such a large group, he was actually shying away from using the full diffeo group. He toyed with another smaller group. Firstly, he toyed with the affine group, which is the group of transformations of this form, lambda x plus b. That's a much smaller group than the diffeo group. And also he toyed with the unimodular diffeo group, that is diffeomorphisms which preserve the volume. All these were shying away from the full power of GR, which needs the full diffeo group. And that's the way he finally formulated it. It turns out that there is no conservation for energy in this theory. Noether's work showed that this was a general consequence of diffeo invariance. Now I'd like you to appreciate that it's coming not from the form of the Lagrangian, but from a symmetry of the Lagrangian. That's what Noether showed. No matter what Lagrangian you use, suppose you had taken R squared, it would not help. It would still have the same diffeo group, and therefore the same problem with energy. Now it took many years to digest this, and I must say that one of the reasons is that at the time when Einstein put forward his theory, the predictions were very few. Just 3 or 4 predictions came out of it. All of them have been verified over the years. But the effects of GR were very small and people moved on to other things. So GR was largely neglected for much of its history until the 1960s. Before the 1960s, in the 1950s, people had developed radio astronomy, and that came from the war because a lot of engineers were involved in making radar systems to detect planes. And after the war was over, they turned their expertise into radio astronomy, beating their swords into plowshares. All the expertise that they gained in the war were applied to science. And when they looked up at the heavens, they could see into the furthest reaches of the universe and discovered that the universe was actually a very violent place. Huge amounts of energy were being released. And it was necessary to use the theory of general relativity to understand those. And even last year, we had an event of two black holes merging together to form gravitational waves. So all this needs all of GR, and it's not just something that should be studied in mathematics, but it's also something that should be studied in physics because it's very relevant to the world. There is no background structure in GR, and all diffuse preserve the action. And we are in the purview of theorem 2. It tells us that all diffuse are generated by 0. The corresponding conserved quantity is 0. And translations, space-time translations, either time translations or space translations, are a subgroup, just as they were in this toy model. And this means that there is no corresponding conserved quantity. There's no law of energy, or there's no law of conserved energy. Now, for a closed universe, this is in fact true. The total energy, momentum, angular momentum, all vanish in a closed universe. In fact, it's also true for the total charge. If I go back to Maxwell's theory, which all of you have studied at some point, one of the equations of Maxwell's theory is that divergence of E is equal to rho, with some constants here possibly. Now, if you work out the total charge in a closed universe, this will be equal to rho dV, which you can use this equation to write as integral of E over the boundary. This is Gauss's law. Now, if the boundary is empty, the charge is 0. So the vanishing of total energy in a closed universe is a very similar consequence that comes out of Einstein's theory. There's nothing very scandalous about that. I did say that there was no background structure in GR, and for a closed universe, this is really true. There is no background structure because we want differential invariants. The only things that we keep constant are the differentiable structure, so to speak. Everything is varied in the action. But if you take situations which are asymptotically flat, you do have a structure at infinity, namely the asymptotically flat metric at infinity. And only things that we recognize as diffuse are those that vanish at infinity. And this is the point made by Logan Icahn a little earlier. So one can define the total energy of an isolated system in general relativity. And this came out of the Hamiltonian formulation, which was developed by Dirac and all that. It's called the ADM energy. It talks about the total energy at infinity for an isolated gravitating system. There are other notions of energy too. For example, if you go to infinity not along spatial directions, but along null directions, you come up with a different notion. It's called the Bondi energy. And the ADM energy and the Bondi energy are both positive, as was shown many years later. It's actually quite a hard subject to show that under reasonable conditions, these physical quantities are actually positive. If they were not positive, there would be a problem with GR because you could extract an infinite amount of energy from an isolated system. You could make the energy go more and more negative, and there would be no energy crisis. So despite appearances, the theory actually makes physical sense. The theory of general relativity does make physical sense. There are other attempts at defining energy in restricted situations. I won't go into them because I think I would like to focus on the personal part a little bit more. There are Komar integrals, which work in specific situations like stationary or axisymmetric. When the gravitational field itself has symmetry, you can try to guess energy expressions. And there are many people who have tried to guess energy expressions either based on mathematical or physical considerations. Now, the fact is, it's impossible to localize gravitational energy. Nevertheless, gravitational energy is real. It can be made to vanish at any point, but it cannot be made to vanish anywhere. The reason for this is that gravitational energy is actually contained in the first derivatives of the metric. There's an affine connection, ABC, which is some expression of depending on g and its first derivatives. And we know that these quantities can be made to vanish at any point. It's a connection. And even in mathematics, a connection can be made to vanish at a point. In fact, it can be made to vanish along a world line. But the fact that it's a connection and not a tensor means that at any point, you can go to a frame of reference in which the gravitational energy vanishes, so you cannot ever localize it. Nevertheless, gravitational energy is real. It is distributed over space, but you cannot say how much is at one point. It's described by pseudo-tensors instead of tensors, and this has led to a lot of confusion. And actually, a very similar thing is also true in non-abelian gauge theories. If you write down the conservation law for non-abelian charge, it looks like this. For example, J mu could be something like this, the isospin generator. I mean, I won't write it down, but J is the current, which if you don't have a non-abelian gauge field, it satisfies this equation, but it's only conserved covariantly, and that means that at any point, if you go to a local frame in which the vector potential A vanishes, then you find that you recover your local charge conservation, but globally, you can't really do much with it. So it's not very different. GR and non-abelian gauge theories are closely related theories. So I'll just close now with a few more, personal remarks about the situation at that time. It appears that Noether's theorems were neglected because physics was not prepared at the time for two important ideas. Those ideas are variational principles and symmetries. Symmetries were being appreciated. In fact, Einstein's motivation was largely to restore the invariance of the physical laws under symmetries, but we didn't have the mathematical sophistication that Noether had to implement these ideas concretely. Many of the developments of modern physics can be traced to these ideas, and let me mention, yesterday Rohini talked about conserved vector currents. That's an idea that came from gauge invariants, and later Shubhra will be talking about broken symmetries, and that is also a very important idea in modern physics. And so much so that it has become almost a reflex. Whenever physicists see a symmetry, they want to convert it from a symmetry of the first kind into a symmetry of the second kind. In the 70s, they realized that the Poincare Lie algebra could be graded. That is, you could take the square root of the Poincare Lie algebra. You have a graded algebra in which you take a symmetric transformation and square it to get translations. So that was an idea that was discovered in the 70s, possibly earlier. I don't know, Loka, earlier? 70s, yeah. So you take the square root of the translations, and that's an idea called supersymmetry, which is a theoretical idea which has been floating around. So what do? They quickly convert this into a symmetry of the second kind. They do it locally everywhere, and they discover a theory which is supergravity, which also is a theory which is very much like GR in the sense that it has a symmetry of the second kind rather than the first kind. Now, here are the remarks about Emmy Noether. She was the daughter of a mathematician, and I realize here there'll be some overlap with what other people have said, including Loka. But I'm not planning to be exhaustive. I'm just picking out a few things. She initially studied languages, English and French, but switched to mathematics because that's where her passion lay. Her work on symmetries is the preamble to her main work in mathematics, that is modern algebra. So from her point of view, this was something tossed off in passing, like en passant, as they say in chess. She didn't consider it to be her main work. I mean, her main work was yet to come. And in fact, she dismissed her own thesis as crap later in her life. She didn't consider herself a physicist at all. And I'll quote some evidence in favor of this. And yet she hugely contributed hugely to physics. For example, in a paper on Noether's theorem, she refers to the physicist's general relativity. In other words, those guys, they have got some theory, which I'm trying to talk about. And there's also a referee report which she had written. And this was a paper by Zaykov, which contained a slight generalization of Noether's theorem, which had actually been done 4 years earlier by Besselhagen. The generalization consists of allowing for divergences. As yesterday, Professor Mukunda said, if the Lagrangian is invariant, but you can also let the Lagrangian have an extra divergence piece when you make a transformation. And this was a paper by Zaykov, which contained a slight generalization of Noether's theorem, which had actually been done 4 years earlier by Besselhagen. The generalization consists of allowing for divergences. As yesterday, Professor Mukunda said, if the Lagrangian is invariant, but you can also let the Lagrangian have an extra divergence piece when you make a transformation. Bessel-Hagen had already done this in 1922. Zakoff in 1926 submitted a paper which, according to Noether, was just it was a very unclear rehash of what was already known. So in the referee report, there are 2 or 3 interesting things. At one point, she talks about the reference that Zakoff makes. He says, the reference to Noether at this point is an error. It should be Bessel-Hagen. So she's taking herself down and putting her students in front. That shows her mental makeup. In a confidential referee report, which will be only seen by Einstein, who had asked her to comment on this paper. Then she went on to say, I cannot appreciate to what extent the integration of the conservation laws, that's the only thing that was really new in the paper, is interesting from the point of view of physics. If that were the case, it might be possible to induce a physics journal to accept this limited part with a reference to Bessel-Hagen. It could also be possible to introduce it in a reference to the statement of my theorems in Courant and Hilbert with an explanatory text. But for that, I must leave it to the physicist to judge. So she does not consider herself a physicist. Nevertheless, her impact on physics is truly tremendous. And this is all just something along with the referee report. Now, she had visited Moscow from an invitation by Alexandrov, who was in Moscow, and was generally supportive of the October Revolution, and like many academics, had Marxist sympathies. She was thus at the intersection of 3 discriminations. She was a woman, a Marxist, and a Jew. Now, in Nazi Germany, the only thing they hated more than a Jew was a Marxist. And women, of course, had a different role in Hitler's view of the world. Their idea was, their job was to produce soldiers to fight in the battles that Hitler wanted to wage against the rest of the world. And she was once evicted from her lodgings because some German student leaders who lived there wrote to the landlord that they didn't want to share their living quarters with a Marxist-leaning Jewess. So this combines all the 3 discriminations. And I should also mention that one of her collaborators, co-authors, Helmut Hasse, who was a topologist, went on to become a Nazi. In fact, he applied for admission to the Nazi party in 1937, but was turned down because they found out he had a Jewish great-grandmother. So she completed her, I'll skip this part because it's been talked about already. She is unpaid for most of her life. And when Hilbert was trying to help her, one faculty member from the philosophical department protested, what will our soldiers think when they return to the university and find that they're required to learn at the feet of a woman? That's a very degrading thing from their point of view. Hilbert responded with indignation. He must have been really bad, stating, I do not see that the sex of the candidate is an argument against her admission as a privat docent. We're after all a university, not a bathhouse. Now, her lecturing style was spontaneous discussions with the students and demanded their active involvement. Not all students could stomach this style of lecturing, but many mathematical results emerged from the lectures. So it was actually a research seminar, in a sense, every lecture of hers, and subsequent discussions and lecture notes. We've heard before that she was generous with her ideas, and many of them were developed and published by others, students and colleagues. And yesterday we heard from Indranil about homology, simplicial homology. Apparently, most of the ideas the fundamental ideas came from her, though as a physicist, I never knew about this because nobody had mentioned Noether's name in that context. She was very popular with the students at the university, was naturally warm and friendly, occasionally critical, which is very understandable, but always nurturing of the talent that she had at her disposal with the students. So here's a picture of her, and my excuse for showing this is that yesterday's picture was more blurred than this one. So that is Hermann Weyl, Emmy Noether, and this is Weyl's wife and son. And I think Krull is also somewhere among the people here. There's also a Chinese student called Sen, who was studying in Germany at that time. So with this, it's not going further, but I'll stop here. The next slide just says thank you. And I think I finished on time. 23 seconds to go.